So in this video, I'm going to teach lesson 6.4b, which is about solving trig equations for approximate solutions. So we'll be using the calculator on these. If a question does not ask for exact answers, then approximate answers are okay. So this would be on the calculator test. You'd be allowed to use an inverse cosine or inverse sine to solve one of these equations. For example, find all solutions on the interval 0 to 2 pi, which means it's asking us for a radian answer, all the radian answers on one rotation of the circle for the following trig equations. We want to start by isolating the trig function, so subtract 1 and divide by 3. And we see negative 1/3 is not one of our recognizable ratios, so it's not a 30, a 45, or a 60-degree angle, or a pi over 3, pi over 4, pi over 6. So we're going to use an inverse cosine to get x by itself, and we're going to go to the calculator to evaluate this with a couple of added complications. First, since we want our answer to be in radians, we're going to have to make sure that our calculator is in radians. So we will go to the document settings, and if it's in degrees, change that to radians, make that the default so that it will stay in radians for a while. Now I can go to trig, inverse cosine, and the ratio was negative 1/3. Problem is, it gives us a single answer, 1.91 radians. So if I go back to my document, I'm going to write 1.91 radians is one of the answers, and that's a perfectly good answer. If we're trying to figure out what quadrant that answer is in, we know cosine can be negative in quadrants 2 and 3. And since this is in radians, it's helpful to think about this as 0 and this as pi, or 3.14. Since the calculator is giving us a decimal version of radians, it's helpful to think about it as 3.14. So you can see that 1.91 is going to be somewhere in the second quadrant, not very far into it, maybe something like this. And there's another quadrant where cosine can be negative, and that would be quadrant 3. So we're looking for, that's basically a reflection down there. We're looking for that same angle, but down in quadrant 3. So if we know that this is 1.91, we have to figure out what that angle is. So there's a couple of ways to go about doing this. The way I think is maybe easiest to see is that it's an entire circle, or an entire 360 degrees, minus the angle that we just found, because the angle that we just found, this 1.91, would be the same as this. So if you imagine this is a complete circle here, if we do 360 minus the angle we just found, then we should have the quadrant 3 answer. But we're not going to use 360 because that's degrees. We're going to use 2 pi. 2 pi is approximately 6.28. So to find the other solution for x, we'll have to do 6.28 minus 1.91, which we can go to do on the calculator. So that's the flaw with using a calculator to do inverse trig. It only ever gives you one solution, and you have to do a little bit of fancy footwork to find the other one. So 4.37 radians as our other solution for x. So these are the two angles that have a cosine of negative 1/3. Similarly, in this tangent equation over here, we're going to start by dividing 3 so we can isolate the tan function. So tan x equals 10/3. And then we're looking on the coordinate plane to think about where tangent can be positive. So tangent can be positive in quadrants 1 and quadrants 4. So when we do inverse tangent on the calculator to figure out what x is, it's going to give us one of those two answers, probably quadrant 1. So we'll go to the calculator and do inverse tangent of 10/3. We're still in radians, so it's going to give us a radian answer, 1.28. 1.28. And that is indeed a first quadrant answer, this one. It's 1.28 here. So if we're thinking about the reflection across the origin here, then this would also be 1.28. So we need to do, in order to figure out the second answer, a full pi, or 3.14, plus the 1.28. So as you can see, each time you do this, it's going to benefit you to draw the picture, figure out which answer the calculator gave you, and then find a way to get to the other answer. So 3.14 plus 1.28, 4.42. So these are the two angles that have a tangent of positive 10/3. To step it up a little bit in difficulty, and this is not a trig equation, as you can see this is a log equation, but it's up here for a purpose. trig or otherwise, you could also use a graph to solve an equation, which is not something we usually do or have done up until now, but we should get in the habit of doing for really complicated looking equations if it's on a calculator test. So here's a complicated looking equation that I think we can all agree we're not going to be totally confident solving this and getting the answers for x on paper. If we have the calculator at our disposal, what we can do is graph the left side of this equation unchanged. Don't touch it, don't subtract anything, don't modify it at all. Just graph it on the coordinate plane. And it's going to create some curve, some wave, it's going to create some shape, some function on the axis, on the coordinate plane. And then you can graph the other side of the equation as another function. In this case, the other side of the equation is just the number 4. So when we graph the number 4, it's going to create a horizontal line. And then we'll be looking for where the left side equals the right side, or where the functions cross each other. So let's see what that looks like. And then we'll see how we can apply this to trigonometry. So I'm going to add a graph page to solve this equation. And I believe the function was a log with base 5. And here there was a fraction, x over x squared. And out here it said plus 5, and I'm not going to put the equals 4. I'm just going to hit enter and let this thing graph. So it creates this log function. And then I'm going to go, on this calculator you can push the tab button, and it'll allow you to type in another function on the same set of axes. So the other side of the equation was just 4, so I graphed that as its own function. And I can see it's a horizontal line. What I'm looking for is where the two functions cross each other, or where they are equal. So if we can't necessarily see it by eye, we can ask the calculator. We're going to menu, analyze, graph intersection point to find where those two functions intersect. We click once on the left, drag it over, click once on the right, and we can see that they intersect at the point 5, 4. Now we know the y-coordinate there is 4. We don't really care about that. It's the x-coordinate we care about, because the equation that we were actually solving, we're trying to solve it for x. So now we know that the solution to this equation, when the left side equals the right side, when x equals 5. And this is a technique that we can use for so many different types of equations. And there are some equations that we'll come across where we actually couldn't solve it by hand and we're expected to use a graph to solve. Now, because this one came out to a whole number, it's likely that we could have solved this one without a calculator. So just for the sake of review, I'll demonstrate how you would have solved this if it had been on a non-calculator part of the test, because we do have the skills, it's just that we haven't seen logs in a while. So here's the equation. We can subtract 5 from both sides, this 5 here, and get log base 5. And while I'm at it, I can reduce this fraction, which is x over x squared, to 1 over x, because one of those x's is going to cancel out. Now I have a single log expression equals a number, and the approach to solving a log equation was to rewrite it as an exponential equation, where this is the base and this is the exponent. So base 5, exponent is -1. It equals the argument of the log. 5 to the -1 power means 1/5, because it's 1 over 5 to the regular power. And now I can see that x equals 5. So this is an equation we could have solved without a calculator, but you have to agree that the graphing approach is a little bit easier if you're not feeling confident in your skills, in your solving skills. So here's a trig example where we can apply it. We have the peak height in meters of ocean waves given by this sine function. And this seems like a really complicated question. But if we get along to the part where it's actually asking us to do something, find the value of t when the alarm first sounds, and the alarm is triggered when the height goes above 12.5. If we can see this thing graphically, we're looking for height equals 12.5. This is the function, and we're looking for time. This is sort of just like solving for x in the previous question. If we can graph this thing and just see when it hits 12.5, then we'll be able to answer this question without knowing much about trigonometry at all. So we're going to use the graphing approach. This function goes in. You see the asterisk over here has a note. Make sure that the graphing angle is set to radians for all trig graphs that we do on this exam, and I'll demonstrate how to do that. And then we'll graph 12.5 as a line that cuts across and see where they intersect. So when I go to a graph, this time I'm going to add a new graph. And before I do anything, I need to make sure the graphing angle is in radians. Now, the calculator's mode is radians, but graphing angles are special. So we need to double check that the graph angle is also set to radians. So once the graph is added, go to menu. And there's settings down here, which is in a different location from the other settings. Here we can see graphing angle is radians. Geometry angle is degrees, and that doesn't matter at all. So the graphing angle being in radians is what we want. We can go to OK, and then we can graph what the right side of this function was, which was 9 plus, click back and see, 4 sine t over 2. But instead of t, we're going to use x because the calculator thinks of the coordinate plane in terms of x and y. So we'll put x over 2. Graph it. We can see there's a wave up there. If you need to change the window, go to menu, window, and change it. And then we need to graph 12.5 as a line. So I'm dragging it up high enough so that I can see past the 12.5. I'll push the tab button so I can enter the 12.5. And now I can see this wave is going to hit that 12.5 again and again and again. It was asking the time when the tsunami alarm first sounds, so that will be the first intersection point here. So we go to menu, analyze graph, intersection, click on the left and right, and we're only looking for the x value, which is our time in this function. So 2.13. We have to check out the units here. In this question, t is hours after midnight. So we're looking at t equals 2.13 hours after midnight. This does not mean 2:13 in the morning, because there's 60 minutes in an hour and decimals are out of 100. So it's fair enough to just answer 2.13 hours after midnight. And then one more, where if it doesn't ask you for an exact answer, and this shows up on a calculator part of the test, you can actually use a calculator to solve this equation as well. And in fact, it's necessary, because we don't have any way to factor this or to combine the sine and tangent together, because they're two different trig functions. Later on, when we learn identities to substitute, there is no way I could substitute something in place of one of these to make this a solvable equation. So we have to use a calculator to solve this. And because it's a complicated equation that I can't simplify, a graphing approach is going to be best. It's looking for all of the solutions for x between 0 and 2 pi. The x-axis, because we're changing our graphing angle to radians, the x-axis is in radians on these functions. So we're going to create this graph 3 sine x plus tan x and look for where it hits 0. We don't have to graph 0 as a separate function because it's already the x-axis, so we just need to look for zeros. So I'm going to add a new new graph to my document. Double check that my graphing angle is in radians, just so you're always in the habit of doing that before you enter a trig function. And the function was 3 sine x plus tan x. Hit enter. It's a crazy looking graph, which is why we wouldn't be able to solve this on our own. And we're looking for all solutions between 0 and 2 pi. For that, I'm going to change my window manually by going to Windows Settings, and I'm going to make my x minimum be 0 and my x maximum be 6.28. If you think about why I'm doing that, that would be the x-axis, which is measured in radians, looking only between 0 and 2 pi. And now I can see there are some solutions. Since it looks like it's intersecting exactly at the 0 and exactly at the 6.28, I'm just going to make my window extend a little bit past, so maybe -1 and 7, just so I can make sure I'm finding those points. So this time, when I go to Menu, Analyze Graph, I just went to intersection. That's not what I meant to do. Menu, Analyze Graph, 0. It's going to find the places where it crosses the x-axis. So indeed, it crosses right at 0. And I have to go back to the menu each time. It crosses at 1.91 radians. 0 again. Crosses here at 3.14159. Oh, that seems familiar. That's pi. Analyze graph again. Menu. Analyze graph. 0. Hopefully you wouldn't get something quite this tedious on an exam. And then it seems like it's doing it again, back at 2 pi. Because this thing is cyclical, it's repeating again and again. So these are all of the solutions on the interval 0 to 2 pi. If it includes both the 0 and the 2 pi, I have to go check back to the question and see if it does. 1.91, 3.14, and 4.37. So it does include both 0 and 2 pi. I can see that because these both have equal signs under them, right? And so I have to give the solutions x equals 0, 3.14, 6.28. Those were the easy ones to memorize because they were 0 pi and 2 pi. And then the other solutions, I believe one was 4.37, and the other one was already forgotten, so I'll check back. 1.91. And that's it for our approximate solutions lesson.